Okay, so we are starting with these notes. We're starting chapter 4. This is the first section of chapter 4, or 4.1. And we're talking about inverse functions. So let's first kind of discuss a little bit about functions. So we're talking, the first type of function we're going to talk about is a special type called a one-to-one function. But before we even start talking really about a one-to-one function, let's think about, we have function f. So we're given that it is a function. And so let's think about, well, what does that mean? For a relationship to be a function, so this is just a set of ordered pairs, right? So we have x, which is the input, and y, which is the output. And we have essentially 5 points, right? 5 inputs, 5 outputs. Now, for it to be a function, can't have any repeated values in the x that have different values in the y. Think about what that would be. That would be 2 points essentially above each other, right? So a point and a point that would be above each other, the same x, different y's, and then our vertical line test would fail. So notice none of these have repeated x values, the same x values with different y values. So this does not give us, function does not, if we graph these 5 points, none of them are above each other. So yes, this is a function. Now, let's flip-flop these. Let's turn all the x's into the y's. So notice this -2 is now the y coordinate of that point. 2, which was the y coordinate, is now the x coordinate. So we flip the x values and the y values for each of the 5 points. And now let's investigate at whether this is a function. So we're calling this reversal, if you will, this flipping, we're calling it function g. And so tell me whether or not that is a function. And you can see there's no single x value that has different y values. So yes, g is also a function. All right. And so that process of flipping the x's with the y's and the y's with the x is called finding the inverse. So g, function g, is the inverse of f, and indeed f is the inverse of g. So if we had started with g and flipped the x's and y's, we would have gotten f. So they are indeed inverses of each other. And since both of those functions, since they're inverses of each other, since they are both indeed functions, then that means they are both what we call one-to-one function. All right. So a one-to-one function is a function. First of all, it's a function, and its inverse is also a function. So if a function, of course, if a function is a function, right? So a function is a function. If its inverse is also a function, then we call both functions would be referred to as one-to-one. So let's look at example A. So they're asking us, are these things inverses? So first of all, not are they inverses, sorry, are they one-to-one functions? So first let's look and see, is number 1, A, is it even a function? And I think you can see it is. You can have 2 x's with the same y, that's a function. But now if we reversed it, essentially if we took the inverse of f, now the arrows are going the other way, and we would have 1 x value with 2 different y's if we reverse this. So this one is no, this one is not one-to-one. The function they gave us, f, that is a function, but its inverse is not a function. So it's not one-to-one. Okay. B. Well, B is not a one-to-one function because it itself is not a function. The vertical line test fails here. So this one is also no. It's not a one-to-one function because, first of all, it's not even a function. All right, next one. So notice here that each x is mapped to exactly 1 y. So each value of the domain is mapped to only one and only one value in the range. So yes, this one is one-to-one. So if you reverse those arrows going the other way, make these the domain, those would be the ranges, and we're okay. No violations there. All right, this one, D. So if we were to reverse these, right? So like I'm looking at this point, and this point. If we were to make the x's the y and the y the x's, all three of these points would have the same x, but different y's. So that would be a problem. Okay? So we'll talk about it more down below, but think about it this way. We have, we talked about that vertical line test to see if it's a function. This is a function, but is it one-to-one? Well, we also have a horizontal line test. So in order for a function to be one-to-one, it has to pass the vertical line test just to be a function. And then a horizontal line test tells us on top of that it's a one-to-one function. All right, and so now looking at this, so this one's a no. And so now looking at this one, clearly the vertical line test is good and the horizontal line test is good. So this one is a yes as well. Okay? All right, so let's play around with this one-to-one some more. And so each x value corresponds to one and only one y value for it to be considered a one-to-one function. And also each y value corresponds to only one x as a result. So one way that we can test this, or we can show, is that if we have two values and they're not the same, so two values of the domain, if they're not the same, then the corresponding range values also will not be the same. So if 1 and 2 are not the same, f of 1 and f of 2 would also not be the same. Okay? And then so different x values give different y values always. Okay. Now, a function is one-to-one if every horizontal line intersects the graph of the function at most once. Like it may not graph it. It may, depending on the function, it may not intersect it at all, but not more than once. So if you can find any horizontal line that crosses it in more than one spot, then it's not one-to-one. Now this one is a function, it just is not a one-to-one function. All right, so a note on something called contrapositives. It used to be this was something that they talked about in geometry, but nowadays they don't really have this in geometry, which is a shame because we use this concept here, but we also use it in statistics sometimes, so it would be helpful if they would reintroduce contrapositives. So we have a conditional. You remember this from geometry. P gives you Q. So if P, then Q. That's a conditional. The corresponding contrapositive that goes along with this conditional is the negation or opposite of Q will give us the opposite of P. And so if a conditional is true, like we have some kind of theorem in geometry, and it's true, then the contrapositive would also be true. So let me think of an example for that. So let's say we have, if two angles are right angles, then what? Then the two angles are congruent. So that's a truth, right? So that's P gives you Q. So if two angles are right angles, then those two angles are congruent, and that's true. Now the converse is not true, right? If two angles are congruent, then they're right angles. That's not true, right? So so just because a conditional is true, its converse is not necessarily true, and in this case, it's not. Two angles are congruent. That does not mean that the two angles are right angles. Okay, now what about the contrapositive? So not Q should give us not P. So let's see this. Not P. So let's say, what's the negation of two angles are congruent? Two angles are not congruent, then the two angles are not right angles. And that's true, right? If two angles are not congruent, then they certainly can't both be right angles, right? So that is a contrapositive. And so if this conditional is true, the contrapositive is also true. So not Q, the opposite of Q, will always give you the opposite of P for sure. If the conditional is true, the contrapositive is always true. So if we know that if two members of the domain are different, right? So if two values are different, A is not equal to B, then F, the output, F of A is not going to be equal to F of B. What would the contrapositive of that statement be? If F of A equals F of B, then A must equal B. And so even though this is our conditional that we know has to be true if we have a one-to-one function, this contrapositive of it, again, logically equivalent, if this is true, this also has to be true. So if I can show this true, if I can show this gives me this, then that tells me that this would also be true and we have a one-to-one. All right, so let's look at an example. So here in A, example 2. So let's start with this. F of A equals F of B. All right, so F of A is going to be equal to F of B. All right, so what is F of A in this situation? Negative 3A plus 7 equals negative 3B plus 7. All right, and we do a little algebra. I could get rid of the 7s, and I get negative 3A equals negative 3B. And then I could divide through by negative 3. A equals B. So since this gave me this, that is saying, oh, then this is also true, because that's the contrapositive of this, right? We said this is the contrapositive of this, but also they're contrapositives of each other. All right, so yes, this is 1, 2, 1. All right, this is 1 to 1. All right, now let's try it for B. So let's again start with F of A equals F of B. We're starting with this. We want to see, do we get this? And if it's true, then we know it's 1 to 1. All right, let's plug this in. We have square root 49 minus A squared equals square root 49 minus B squared. All right, so we could square both sides. 49 minus A squared equals 49 minus B squared. I think you could see we could subtract 49 from both sides, and then we could also multiply through by negative 1. So eventually you're going to get A squared equals B squared. Now, does that automatically give us A equals B? And if you think about it a little bit, I think you'll see that no, this, if we know that this is true, but we do not know that this is necessarily true. Because think about, what if A is 2 and B is negative 2? That would be true, but A equals B is not necessarily true. All right, so this F of A equals F of B does not give us A equals B. Not for this particular problem, right? So this is not true for us for this particular problem. And so this is not true, and as a result, no. Not 1, 2, 1. Okay, for part B. All right, So that's kind of a formal way of looking at it, but ultimately you really just need to be able to look at a graph and say whether it's one-to-one, and look at a mapping and see if it's one-to-one. Okay, so let's go on to number 3. Talking more now about inverse functions. So we're given a function f and given a f of x and another function g of x. So find f of 10 for me. So what is f of 10? So f of 10, you put a 10 in here, I think you see you get what? 85. Okay. Now find g of f of 10. So that's the composition, right? So we're now, the output for f of 10 was 81. So now g of 85. So we put g into 85. This is 1/8 times 85 minus 5 over 80, 5 over 8. So 1/8 of 85 minus 5 over 8. And what does that give us? That gives us, well, this would be what? 80/8 or 10. So it's interesting that the input in the original function, so essentially what did we just do? We did f of g of 10. No, sorry, we did the other way. G of f of 10, right? And we got 10. Isn't that interesting? The input was 10, the output was 10. All right, let's try a couple more. What is f of 3? So putting a 3 in for f, I think you see we get 29. And then if we put 29 into g, I think you see we get 3. And let's try one more of those. So in other words, g of f of 3 equals 3. And let's try 2. Let's do the reverse now. This time we're doing g. So now, and then we're going to plug that in. So we're really going to do f of g of 2 this time. Right? That's what this is asking. So what's g of 2? We put 2 in. We get negative 3/8. And then we do negative 3/8. When we plug that into this, right, the 8's going to cancel with the 8 on the bottom. Negative 3 plus 5 is 2. So that's equal to 2. Now let's, instead of putting values in, instead of doing g of f of 3 and finding that it's 3 and f of g of 2 and getting it to be 2, let's just now keep it as x. So g of f of x, so I'm going to put the whole function of f in here now, 8x plus 5. And now I take and plug this whole function in for x here. So this is 1/8 times 8x plus 5 minus 5/8. All right, so distribute the 1/8 to this. That gives us x, and plus 5 over 8 minus 5 over 8. Notice that's x. So this is just equal to x. All right, now what's f of g of x? So now f of, and I'm putting this whole function in, 1/8 x minus 5 over 8. Now I'm taking this whole function, plugging it in here, 8 times 1/8 x minus 5/8 plus 5. And so when I distribute the 8, that's just going to be x. The x, and when I distribute the 8's going to cancel. That's minus 5 but plus 5, and again, that's equal to x. So notice this is kind of unusual. These two functions, regardless if I do if I do g of f of 10 or f of g of 2, in each case I get exactly what I started with. And then maybe it's just kind of a coincidence for those numbers we plugged in, but now generically we put in just x. So the input of x is the output of x, and it doesn't matter if I do g of f of x or f of g of x, I get the same thing. And so this is a test, a way of deciding whether or not these two functions are inverses of each other. So they will be inverses, so function f and function g, of course they have to be 1-to-1, and g is the inverse of that function if f of g of x is x and g of f of x is x. Now remember, these are the sort of the new ways that we learned a couple chapters ago, or last chapter, how to do composition of functions. All right, back when we did compositions. We can do fog x or we can do golf x, but most people have an easier time thinking of it as f of g of x or g of f of x. All right, so let's go on to page 2. So we're looking at page 2 now. All right, in example 3, g of x was the inverse of f of x. We have a special notation for this inverse notation, this inverse of a function. So we have f of x is equal to this. Instead of calling this just g of x, we could call it f, the inverse f of x. Inverse of f of x. So this looks like an exponent. This looks like x to the negative 1, which is of course 1 over x. But that's not. This is not equal to 1 over f of x, right? It's not the reciprocal. This is referred to as the inverse function. So this is the inverse of f of x. Now you'll know, I mean, you just have to know, like, well, how do we know when it's an exponent and when it's an inverse? You'll just know from the context of the problem. I mean, obviously this is a function and it's got an exponent, so this is the inverse of f of x. All right, so we don't say f to the negative 1 power. We don't say the reciprocal of f. We say it's the inverse of f of x. Okay. So find the inverse for number 4. Find the inverse of f of x. So they give us a function here. Find its inverse. All right, so remember, when we saw this on the other page, we turned the x's into the y's and the y's into the x. So the inverse of f of x is simply going to be 3, 2. It's going to be 5, negative 4. It's going to be negative 5, 4. And lastly, 1, 3. All right. So we're simply replacing the x's with the y's and the y's with the x. All right, here's another function. This time they gave it to us sort of as a mapping or a table. What is the inverse? Well, we could just make another table if we wanted. And we'll call this x. We won't call this h of x. We'll call this h, the inverse of h of x. All right, let's put some lines in here. All right, so now we're going to have the h of x, or the y, now becomes the x. So negative 1, 2. The y, or h of x, negative 4, now becomes the x, 5, 0, 9. Okay, so remember, this is the inverse of h of x. All right. Steps for finding the inverse of a function, which of course is 1-to-1. So if the function's 1-to-1, then its inverse is also going to be a function. All right. So first of all, if we want to try to find the inverse of this function, we replace the f of x notation with just y. Y and f of x are kind of the same thing, except just because it's a y does not necessarily mean it's a function. But with f of x notation, it's sort of denoting that, yes, this relation is indeed a function. But for the meantime, replace it with y. All right, now the inverse. We replace the x with the y and the y with the x. So x equals 3y plus 2. Now this right here already is the inverse. If we were to graph this thing and graph this thing, we would see, and we're going to see that down below when we graph it, that they are inverses of each other and what that means graphically. However, to graph this thing, we don't really want it in this form. We want to solve it for y. So move the 2 over. What? X minus 2 equals 3y. Now let's rewrite it with the y on the left and also divide through by 3. Y equals 1/3 of x minus 2. All right. I could have divided it by 3, but we're going to see we want this kind of in slope-intercept form. This is a line, right? And so this is also going to be a line. So really, we want it in y equals 1/3 x minus 2/3 so that we can graph this thing. And then finally, the last thing is to rewrite it and take out the y and put in the inverse of f of x. So the inverse of f of x equals 1/3 x minus 2/3. So again, we could have written this instead. We could have written this as x minus 2 over 3, right? That's perfectly fine too. But for graphing purposes, it's probably better to leave it in slope-intercept form. All right, so let's now graph this thing. So don't mind this thing. We'll talk about this in a minute. This is called the identity line. This is the y equals x line. Goes to the origin, has a slope of 1. It's called the identity line. Because if x is 2, y is 2. If x is 3, y is 3. So x and y are identical in each point. So that's why we call the identity line. All right. So let's graph the original thing. So we're going to go y-intercept of 2, slope of 3. So y-intercept of 2, slope of 3. Well, I can't really go up, so let's go 1, 2, 3 down and 1 over. 1, 2, 3 down, 1 over. I would be about here, I guess. So let's sketch that in. And put in our lines, our arrows. Okay, so that is the f of x. Let's label that, f of x. Okay, now let's do the inverse. So we have a slope, we have a y-intercept of negative 2/3. So that's about here. Now we can go up 1 over 3, which would take us here. But let's think about this. Since the y-intercept is fractional, let's see if we can get back onto a corner. So let's think about, instead of saying rise over run, can we think of it as 1/3 over 1? So I'm going to go up 1/3. I'm now at a negative 1/3, and I'm going to go over to the right 1. So I would be about right here. If I went up another 1/3, I'm now on the x-axis, go over 1, I would be here. So now I'm kind of like on a corner, and so now it's a little bit easier to see, oh, I go down 1 over 3, there's a point that's on our line, down 1 over 1, 2, 3, and so let's put it about there. Okay, so let's sketch this in. So rather than creating like a point here, going up 1 and creating another point here, sometimes it's nice to get back onto a corner. It makes it a little easier. All right, so let's sketch that one in. So that looks like this. And of course, put arrows. Now notice, if we put the identity line vertically, now you can see there's a really good symmetry between these points. And also notice, let's look at a couple points. This point was 0, 2. Notice on the inverse, we have 2, 0. Right? That's not a coincidence. The x's become the y has become the x's. Also, the point where the line crosses the identity line, that's -1, -1. The inverse is -1, -1. So this point is its own inverse. And that makes sense why both of our functions, the function and the inverse of the function, both cross at that point. So this, let's label that. That's the inverse of f of x, this line here. Okay, does that make sense? All right, let's go on to part B. We've given a function, and we've also been given a domain restriction here. X must be greater than or equal to 0. We'll see why in a minute. All right, so let's go through the process. Replace this with y. X squared minus 2. Now replace the x with the y with the x. X equals y squared minus 2. Solve that for y. First of all, for y squared, move the 2 over. X plus 2 equals y squared. Now we want to solve it for y, so let's bring it over and take the square root of both sides. Y is equal to plus or minus the square root of x plus 2. All right. However, you have to really be thinking a little bit about this. So if we were to just graph this thing, ignoring this, if you remember, that would take us down to what? That would be a vertex at 0, 2, 0, -2. It would be down here. And it's a basic parabola, but we do what? We do one here and one here, and then we go over 2, up 4, 1, 2, 3, 4. It would be here, and then we'd be over here as well. So if we didn't have any restrictions on the domain, then we would have this parabola here, right? Something like that. But we have a restriction. The x must be greater than or equal to 0. So that means we do not have this bottom half. And why we do this? Because, first of all, the function, g of x, not f of x, g of x, our function, has to be 1 to 1. So we know we're limiting just the 1/2 of that parabola. So this is our function. That is our original function. And this is why we're restricting it here, because this has got to be a 1 to 1 function. And if we didn't restrict it, the horizontal line test would fail. It would not be a function. It would not be a 1 to 1 function. Okay, and so now we know that this, we have to be careful now, this is a sideways parabola. This is a radical, right? So this is like half of a sideways. So we can't have both of these. We can't have both plus and minus because we have some restrictions. So let's think about which one would we have. So if we graph this thing, it would be starting over here at -2, and it would go here. So let's put our points in here and here, and then over 1, 2, 3, 4, up 2 would be this point. So we've got this, and then we'd also then have the bottom half. But you can see we only have the right half. You can kind of see by looking at this, obviously we've got the correct side because this is symmetrical with that through the identity line. So we can look at that clearly. We should not be plotting the other points here. We should not be plotting the other half of this parabola. Okay? So how do we restrict that? Well, we don't want the bottom half, which would be the negative. So in this case, we don't want both of those. We only want the plus. Okay? All right, so now let's write it in the correct notation. We kind of forgot to do that. The inverse of g of x equals the square root of x plus 2 with the plus only. Okay, we don't really need to write the plus, but just to emphasize it, it's there. Okay? And so you can see, let's kind of draw that in a little bit better, but you can see that there's a nice symmetry there. And you can see This point, which is 1, -1, became -1, 1. This point, which is 0, -2, is -2, 0. This point is on the identity line, so it is an inverse of itself, right? It reflects upon itself. Okay. Last one, C. So again, y equals x minus 1 over x minus 3. That'll give us some restrictions here. Or x cannot equal 2. I'm not sure why that says x cannot equal 2. It seems like it should be x cannot equal 3. I think that's a typo. I must have changed the problem and didn't change. You could certainly put a 2 in there. Yeah, it's got to be x is not equal to 3 because it would make our function undefined. Okay, so that's a typo. All right, so now we replace the function notation with y. Now we write x equals y minus 1 over y minus 3. Now we got to try to figure out how to solve this. I would say pause the video and see if you can figure out how to get y by itself. All right, I'm going to proceed. So we're going to multiply both sides by this denominator. So we get x, y minus 3x equals y minus 1. Okay, so I multiply both sides by y minus 3, distributed the x to both of those. And now I want to move the y's to one side, the non-y's to the other. We get xy minus y equals 3x minus 1. Factor a y out. We get y, and then x minus 1 equals 3x minus 1. And then finally we'll divide by the parentheses. Y is equal to 3x minus 1 over x minus 1. All right. So, and then finally, let's write it in the correct notation. The inverse of h of x equals 3x minus 1 over x minus 1. Now notice the x was restricted here. That means the y is also going to be restricted, right? I mean, the thing that gave this a 0 is what gives this a 0, right? No, sorry. Sorry. That was confusing what I was just trying to say. So we have the denominator, right, restricts here. What we really want is on this one, the restriction is going to be x cannot equal 1. All right. So we know this function. This function is a rational function, and we're going to have asymptotes. Now I already graphed it, the two functions for us, just so that it was kind of easy. Otherwise, it would be a little bit crazy. But the first one is h of x, which is down here. Notice it's got a vertical asymptote at 3. So you can see here's 3. Right? That is our asymptotic function here and here. Okay? So the restriction on that one at 3 is where the asymptotic function is for the other one. So let's see, hang on. We have, for this one too, we have an asymptote here. I'm going to change the colors now. For the inverse, let's sketch that one in red. This is the inverse, so that one is red, and it is also here. Okay, it has a restriction at 1. X equals 1. X cannot equal 1, right? So that's an asymptote. Just like up here, x could not equal 3. That was the vertical asymptote. But This, the original function's horizontal asymptote of 1 is where our vertical one is now. Remember, this was y equals 1 and had an x equals 3 in the original function. Now, the asymptote, horizontal asymptote for the inverse, that's y equals 3 because the x becomes the y and the y becomes the x, right, because of the inverses. But you can see, I kind of made a mess of all this, but you can see how now there's a really nice symmetry about the identity line. All right, so besides these, we are going to also be talking about, like, what's the domain, what's the range. So the domain here is any value, x cannot equal 3. The range, if you think about that, what restriction do we have there? Y cannot equal 1 would be for the range. I guess I should be doing that in black. Okay, y cannot equal 1. All right, then down here, the domain is that x cannot equal 1, and the range is that y cannot equal 3. So you can see how the domain, this one was the domain up here, the domain, x cannot equal 3, became the range in the inverse. The range at y cannot equal 1 became the domain in the inverse. Okay? So that'll hopefully, we will be talking about some domains and ranges, just like because the x and the y is flopped, the domains and the ranges, which are the x and the y's, they flop as well. Okay, so you have homework here. Due next class.